we're all set. Okay. So thank you everyone for coming. So today I will explain about what my whole PhD is about and what I've been doing these months here at the EU. So just to put you maybe a bit of context. So the ideas I will talk here are like very based on like John's ideas. That's why the reason I come here. Also, Lou, John have worked like closely with my company some years ago, and that's what the relationship with my company. Also, that's why context why I'm here. So the agenda for today, it's first to explain you, okay, what's my PhD topic about and why it matters. So all these months in September that I've been sitting at Scott's desk, what have I been actually doing and what are the results? Then I will show you a quick demonstration of some tool I implemented. And then finally we can have like some sort of questions and you can ask me whatever you want, okay? So let's get started. So this schema here that you will keep, you will see many times in this presentation, but this is the standard deployment of mobile networks, right? So we have a mobile device that connects to a base station, and then it connects to the core network of the operator, right? And then eventually you reach the data network or the internet. Okay, so this setup, let's say, it's what we had in previous generations, okay, in 3G, 4G, 5G. And the main goal through all this generation, it was to reach that a packet leaving the mobile data network, do it as fast as possible. So 3G started doing this, 4G already does it really good, 5G, you don't notice the difference, right? So yeah, but in 6G, the paradigm, like the scenario seems to change a bit. So in 6G, we're moving more like the scenario that we are seeing, it's the so-called network of networks. And it looks more a bit like this. So what would we have in this network scenario? So we're starting to have networks of cars that drive by themselves. We have satellite networks, or we have 5G networks with 6G networks, and all of them different operators, and they need to be interconnected between them, okay? So the actual question is like, okay, so we had this works, we know that we are in a good position with that, but how we move from this scenario, like what technology we need to support this scenario, and moving from this one, okay? And answering this question is what about my PhD is about. But before giving you more details, let's take a look, just a brief history on network protocols in the mobile, okay? So this is the protocol in 3G, okay? Don't worry, we'll not get into detail, just get the picture, okay? We have some red layer here, TTP, Parpel, and PDCP, okay? And that was 3G, okay? Well, the first commercial deployment was in 2001. Now, keep this in your mind, then we move to 4G. Nothing really changed, right? Some letters change here, some stuff, they change some things, but essentially the protocols are, well, essentially no, they are exactly the same, okay? 5G, they added some extra layers here in the radio segment, but essentially, like in 30 plus years of mobile history, protocols didn't change, but the scenarios and the use cases, yes, right? So we're moving from this to this. So what we're proposing here is like a technology that might solve this transition, and we call it 6G-RUPA, okay? 6G-RUPA stands for 6G Recursive User Plane Architecture, okay? And it has three main goals. One, it allows network to be much more scalable. We will go in detail into that later. Two, it allows federation between networks, okay? So it actually implements real internetworking, communication between networks, comparing to the actual roaming that we have. And then finally, and this is very important, so it allows the networks to be designed and implemented to adapt the environment they serve. So what does it mean? So imagine that you have a kitchen, okay? You have your kitchen tools and your ingredients. So if it's winter, maybe you will like a warm dish. And if it's summer, you will like a cold dish, right? So you have the tools to build networks, to your network the way you want, okay? With 3G, 4G, 5G, you just take the specification and you need to apply that. You don't have this flexibility. So 6G-RUPA provides you with flexibility. Just to be more concrete, so some issues with 5G. First, again, this is the typical scenario, we have a mobile phone that connects to the operator network, and then it reaches the internet, okay? So in order to the operator to reach, sorry, the mobile phone to reach the operator network, it needs something like this, okay? And this is a tunnel. So, and this idea comes from the very early days of the telephone, where if one user want to call another one, like someone in the middle, like a woman in the middle, needed to put the cables and make like the physical connections. So this is what we have nowadays. Okay, something changes, but at the end we have virtual circuits. Okay, and we know from the early days of the internet that virtual circuits they don't scale that well. Okay, so scalability is an issue with 5G. Then the network federation mechanism are weak. So let's put another example. Okay, so I come from Spain, I come from Barcelona. So imagine that, okay, I'm here, I'm with my Spanish SIM card, okay? And with my phone, in order to connect to the internet, what will happen is my phone first connect to the American operator, let's say through Verizon, and then it needs to go to my operator back to Spain, and then it will reach the internet, okay? And how the network does it. So it builds not only one tunnel, but two tunnels, okay? Again, we have the problem with scalability. And imagine, so this kind of works for two operators, but if you're having this, you really want to connect all this network between them, doing like mesh network with tunnels. You can see that does not scale very well. And finally, 5G is one size fits all. So you take the specifications and you apply it. That's it. You don't have that much flexibility. Okay, and how this compares to 6G-RUPA. So, for example, in 6G-RUPA scalability, basically, you're not forced to use virtual circuits. I mean, you might use them. If you have an application, for example, that you're streaming 4K video and you really need like specific quality of service, then yes, you go and use virtual circuits. But if you have like a factory full of IoT devices, then you don't need a virtual circuit for every IoT device, maybe, right? Also, the InterNetworking model versus roaming. So roaming, we showed it does not scale really well. So 6G-RUPA provides the InterNetworking model. Okay, so the idea of the InterNetworking model is that you would have like the American operator network here, Spanish operator network here, and then on top of that, you have like a network that helps communicate these two networks. Okay, and you can have like many sub networks here that are communicated through the federation network. Finally, as I was saying, layers are basically programmable, so you can program the networks. Okay, you have a framework, you have the tools, and then you easily can build your networks the way you want and the way you need. In summary, 6G-RUPA provides better scalability, and you will see a great example about that very soon. It provides much better, much simpler, much elegant InterNetworking mechanism than roaming, and it's more flexible. So yeah, you just basically have the ingredients, the tools, and you build networks specifically tailored for the use cases. And in fact, one of the most, one extra one. So if you scale well and you adapt your networks to the physical nature, you are more efficient, so you're greener. Okay, that's an extra point. But if I want you to keep like one thing, in fact, 5G, 3G, 4G, it's just a subset of 6G-RUPA. Okay, that means that 6G-RUPA is just a generalization of 5G. Okay, you could implement 3G with 6G-RUPA. Okay, so yeah, that's it. Okay, so that was for the introduction to 6G-RUPA, and now we will take a look at scalability, the problem with scalability. Okay, because this is what actually I have been focusing on these 3 months. Okay. So okay, first, what's the scalability? It's like a broad term. So what is actually the problem we want to solve? Again, we have this graph, and this is the mathematical form of the problem we want to solve. Okay, let me explain you. So f, it's the forwarding function. Okay, it's the function that tells the router, okay, when I get a packet, I will put it in this interface or in this other interface. Okay, so the forwarding function will get the information of a packet, and then with this information, it will decide the output port, the output interface to where to put the packet. But we're missing one letter here. Okay, it's the S. And in fact, the S is the actual problem we want to take a look at. So the forwarding state function. So the S, it's the forwarding state information needed by the forwarding state function. Okay, what does it mean? So it's the needed information for a router to execute the forwarding function. In other words, it's the needed information from moving one packet from one interface to another interface. In 5G, what's the expression of this S? So as we were saying in the beginning, in 5G, we have one tunnel. Okay, we saw that. But we don't have one tunnel per every connection. We have two. One for the uplink traffic, the traffic that goes to the internet, and one for the downlink, the traffic that goes back to the mobile. And we have this information for every mobile phone, okay, for every user equipment. And that expression, okay, that's the information state that the router needs in 5G. Yeah, by the way, the router is called UPS, okay, so we can call it router for us. And 6G-RUPA, the same state information unit. It's first the cost of a forwarding entry, okay, and this cost it's not for every user. Okay, this cost it's for every neighbor. Okay, we will see what that means. So at this point, I think half of you might be like disconnected already. So let's do a quick quiz. Okay. Again, we have this scenario. Okay, we have the router here. We have the expression of 6G-RUPA. What's the value for this scenario? What's the value of number of neighbors for the router? Who knows the answer? A hint? No one? It's 2, okay? So the value of the number of neighbors is 2, because the router has basically two neighbors, one base station and one data net. Okay, let's do another one. Now the scenario changed a bit, okay? We have 3 phones. Again, this expression is the number of neighbors. What's the value of this? Anyone wants to try?
You still have 2?
Okay, with a sheet. 2, okay? So, I don't know if you notice what happened here, but in 5G, the state information, it depends on the number of mobile phones, okay? So if we put numbers to this expression, that would be 3, because we have 3 mobile phones, 2 tunnels for every mobile phone, cost of every tunnel. And in 6G-RUPA, since you only depend on the neighbors, you will have 2 times the cost of forwarding entry. You see what's going on here, right? So in summary, in 5G, that's the expression. The complexity of the expression grows with the number of users. Okay? If we put this in the big O notation, which is the standard, it's the complexity is On. Okay, it grows linearly with the number of mobile phones. And in 6G-RUPA, it depends on the number of neighbors. Okay, and the number of UEs it's way bigger than the number of neighbors. So there is much more mobile phones than antennas out there, right? So the complexity of the state function in big O notation is O1. So essentially, like the state information you need to do the same function, here it works. It grows linearly, and here it just stays constant with the number of users. Let me do you like a bit of a spoiler, but when you put this like in a very big scale, like in a national operator network like Verizon, when you have a very big network, you end up having with this, okay? For example, this the Verizon network is all the state information you need, okay, for running the network. This is in 5G, this is in 6G-RUPA. Okay, so basically we have 3 orders of magnitude of difference. So we are saving like memory from the order of gigabytes to megabytes, which is a nice result, right? So we're done with the second part now. I did a spoiler here, but now I will explain you how I get to that point, okay? How I get these numbers and how the number comes, so you can trust me. And I just don't show you just like a plot. So in order to actually like build national operator networks, I implemented a simulator, okay? The name of the simulator might not be the best one, but it's like PLMN, which it stands for Public Land Mobile Network Graph Simulator, okay? And that name has a reason, and the simulator has two goals. One is to build a network topology graph that emulates the infrastructure of national rate operators. So for example, Verizon, you just want a graph that simulates the infrastructure of the operator. And then once you have like this big graph set up, you just simulate dynamic usual connectivity patterns in order to see how the network behaves. So let's see how we achieve that. Okay, we will go step by step. Let's see how we can build a national rate mobile operator graph. We'll start from this schema here. So first thing, the easiest thing to put is the base stations, okay? So the operators are very confidential with all this data. But for the base stations, there is a data set that it's open. It's called openslavely.org. And basically, it's users reporting where the base stations are. The data set includes the location, so we just have to put this in a map. That's a very easy one. So let's do that. Okay. And we'll see for the United States. Okay. I removed Hawaii and Alaska because they were just too annoying to plot it everything, but yeah, you get the idea. So we have the base station here. Now the mobile phones. Okay, the mobile phones, it's a bit more tricky because you basically need to get the data from a trustable source. Okay, so for the United States, what I did is that I went to the Census Bureau public data. I got like the total inhabitants of the United States, the inhabitant per county in the United States, and also the size of every county. Okay, and that way, playing a bit with the data, you can basically put where everyone lives, more or less. Okay, so here we have the two things now. The blue dots are the people. Every dot is, I think in this picture, every dot is 10,000 people. Okay, every dot represents 10,000 people. That way it's easier to simulate. It would be impossible to simulate like the whole population of the United States. So we have now the base stations and the people. Okay, now we need to add the main routers because that's what we actually want to measure. So we have a problem here because, as I said, like the mobile network operator keep this data very confidential. We know, like we tried to contact Verizon. Scott helped me like to see if they could give us some data set to play and everything, but they were really not giving us much. So what we do is that we just deploy them in the optimal way. Okay, and by optimal way, I mean that so the number of routers, it's a parameter in the simulator. You say, okay, I want 10 routers, and these 10 routers are placed in the closest chain of B as possible, okay? I know that there's some data science people in the room, so I do that applying the k-means algorithm, okay? But just keep that. So these are placed in the best possible way. And the best possible way, for example, I don't take in account rivers, mountains, roads, so it's just in the more or less. So that said, I decided a number for the UPFs that made sense. So I decided 800 something, which is the cities in the United States with more than 40K people, but you can play with that. Okay, you need to, if you place in the map, they look like this. United States is a very big country. It's a bit hard to visualize. So I also did this exercise for Spain. And in Spain, you can understand more what's going on, right? So you can see how the UPFs are like closer where the people live. Like this is Madrid, this is Barcelona, many UPFs are here, and here it's a bit more empty, so the UPFs are more scattered. Okay, we're just placing them in the most optimal way if you could place it whatever you want, without thinking about the mountains and everything. Okay, and now we have all the elements, and now to build the graph, we just connect the dots. Okay, so we just get the phone to the closest base station, the Euclidean distance, and then the base station to the core network. And then we have a graph. Again, United States is very hard to visualize things. So for the Spain, which is a way smaller country, you can see actually the graphs. Okay, so the base stations connected to the closest UPF. Okay, good. So we have the graph already. And now we can perform simulations. Okay, we have the graph, and now we can simulate. So what we are simulating here is that we're simulating like regularly uses with a phone, like us with a smartphone. This is called eMBB in 5G. But that means that every phone, every user, like all you here, you have 1 to 2 PDU sessions active per phone. Okay, you have one session for the internet stuff, and you have another one for calls. Okay, it doesn't matter if you don't have if you're not having a call, but your phone already sets up the PDU session, so if you get a call, you can get it quickly. Okay, so we're simulating this. All right, so if we do the simulations, I did it here for a bunch of operators. Okay, I did it for AT&T, T-Mobile. So this is the US. This is the Spanish operators. Again, so the big take here is you have 3 orders of magnitude. Okay. One could say, okay, yeah, but with the memory, because this is exactly like the memory size that the implementation in the simulator takes. So one could say, okay, but memory, this is very dependent on the implementation you are doing. Okay, it might be. So we can just look at the entries, we just look at the forwarding tables, and then we measure the entries that the 6G-RUPA one and the 5G one have. Okay. So still we see it is proportional. Okay, we see a very big difference. Yeah, and this is another one. So you see the distribution of the size of the forwarding tables for all the UPS. Okay, just to have more understanding more what's happening. So yeah, so some conclusion was about these results. One is that hardware acceleration becomes impossible. What does it mean? So if you want to implement 5G router in a FPGA-based high-end routers, these routers that go very fast, you just can't. You need too much memory, so you cannot do them in these high-end routers. Okay, you need to do it in some commercial servers because it will not fit directly. Second important take here is the zero marginal cost of users. And what does it mean? So if you want to add users to your network, it doesn't cost you anything in terms of memory. Okay, so if you have your network and then 10,000 users come, okay, maybe you need to add 1 and 10, 1 G node B, but in the UPF, they don't feel it at all, the fact of adding new users. Yeah, and as I said, no, so you are doing the same thing, you're just reducing from gigabytes to megabytes. This is quite nice. Okay, this is quite a good result. So yeah, that was mainly it. So if you want now, I could do a quick demo on how the simulator works so you can get the idea, and I can explain you a bit. So let's see. Okay. So as I said, the simulator, okay, first thing is that you can configure it through this configuration file, okay? So you can say, you can play with, for example, with the scale factor, okay? So you can say, okay, how many people do you want per agent? Okay, so one agent, it's 1,000 people on 10,000, okay? The biggest the number is, the fastest the simulation will run. Let's do 10,000 because it will run quicker for the demo. You can play with the duration of the simulation. You can play with the time that every session will last. So here we're just simulating that the user arrives, it connects, and it stays connecting. Okay, that's what we're simulating, which again is the regular use for our smartphones. Yeah, some low level like the time, the sampling that when you're measuring. And here you can play with the countries, okay? For example, I have implemented Spain and the US. So you can add here the total population of the country. Yeah, okay, you can play with that because, okay, not everyone has a mobile phone. So you need to, okay, from all the people, just 82% of the people have a mobile phone. So you need to play a bit with that. But yeah, so let's do a quick simulation. So let's select one operator from Spain. Movistar is one of the major ones. So let's do, for the US, let's do Verizon. Okay. And yeah. So we'll run it. Okay, just run the main. Oh. Wait, I'm not in there, right? Yeah, now it worked, okay. As I said, you can do basically, it's very simple. You can do two things, okay? Either you can draw these nice plots that I was showing, or you can run the simulator. So let's run first the plots. Okay, well, it generates, because there's a lot of data, so it takes a bit, but the good thing is that I decided to implement this in Julia. I don't know, to be honest, I didn't know this programming language, but it's some sort of very abstract level language. But at the same time, you get really good performance like in C. Okay, so you get the best of two worlds. Something like Python, but it's fast. Okay, yeah. So this is for Spain. Now it should run the US. It can take a bit longer because there are much more data. And it can run everywhere. So this is like running directly my laptop. So no like super powerful server nor anything. Okay, yeah. And it generated the images, so you can look at them later. The other thing that you can do is just run the simulation, okay, that you just choose. So we run the simulator. We will see like all the events happening. Yes, now it's doing the Spain. It's doing it for Movistar. Yes, for example, in the case of Spain, there's 46,000 base stations, then 52 UPF because it's a number that makes sense in Spain because it's the number of like counties, let's say. And then for the US, okay, we have way much more. Do you know this? Okay, and that's it. So that generated the results in CSV, so you can check them later. You can do the nice. You can treat them like as you want. So for example, we have the time in the. Yeah. Okay. So we have the time of the simulation, then every UPF. We have here like the number of entries of the forwarding table. We have here the memory of all the entries. And the same for 6G-RUPA. Okay. So yeah, so that was basically it.